Hello again, Mark Voit here. This is video 2, and it's about something I realized when responding to the first referees report on the paper I talked about in video 1. And it caused me to write an erratum to the Voit 2017 paper, Voit et al. 2017 paper on precipitation. It's not yet on the archive. So this figure is from the paper I talked about in video 1, so please see that video first. But one of the things we were puzzling about when writing the 2017 paper is where does the wave energy go when an internal gravity wave damps? It continues to be pumped by thermal instability. The energy has to go somewhere. Well, back in 2017, in the paper, we appealed to resonant triad interactions. So that's what happens when you have a wave that resonates with another wave pair that might start with infinitesimal amplitude. But as that resonance happens, you can channel energy from the original wave to the other wave pair. And you can estimate the damping rate. And from the damping rate, so the damping rate equal to the 1 over the cooling time, you can get a saturation amplitude for thermal instability that turned out to be consistent with the one observed in simulations. In the 2017 paper, because internal gravity waves exciting other internal gravity waves doesn't seem to get rid of gravity wave energy, I thought that the secondary waves had to be sound waves, which are stable and damp through radiative cooling. But I turned out to be wrong. And so that's why I wrote an erratum. So when I went back and looked through the literature on Earth's atmosphere, I learned that there is this criterion for nonlinear wave stability. And this is a very elegant paper by Hasselmann from 1967, where he showed in resonant triad interactions, there can't be net energy transfer from lower frequency to higher frequency waves. So even if the sound waves have a beat frequency that's equal to the gravity wave frequency and couple, so you get coupling of the strength we estimated in the 2017 paper, you can't get net energy transfer over time. And so this channel doesn't work. So what actually happens? Well, the atmospheric and ocean scientists know all about this. There's something called subharmonic parametric instability. And so a gravity wave can decay into lower frequency internal gravity waves that propagate at a steeper angle, not so horizontal. And that turns into sort of weak gravity wave turbulence, or you could just think of it as nonlinear mode coupling that sends gravity wave energy into lower frequency gravity waves. And ultimately, those gravity waves break and you do get Kolmogorov turbulence then, but there can be a lot of wave number space where what you're getting is gravity waves decaying into other gravity waves. And I'll pick up on that in video number 3.